Welcome to my talk. I'll be mostly talking about particle tracking and turbulent dispersion and high Reynolds number that we have been doing on Blue Earths. Before I begin, I would like to thank and acknowledge the support from NSF and the help, like all the help that we got from Blue Earths team and Gray and our co-PIs and collaborators and the other lab members in our group. So what is turbulence? As everyone knows, it's one of the most common state of motion of fluid in both nature and engineering. It's pretty much everywhere, and it's always characterized by a very wide range of disorderly and non-linearly interacting scales, and it's always unsteady and three-dimensional, and always occurs at very high Reynolds number. And one of the key features of turbulence is that it causes very high increased rates of mixing and dispersion, which is a key thing in most environmental and engineering problems that we encounter. And without going into much details, like one of the tools to study turbulence is direct numerical simulations, where we resolve all the relevant spatial and temporal scales, but this comes at a very big price, and the cost of it goes as the Reynolds number to the power 3. So of course we need a lot of computing power to do DNS. So, and coming to turbulent dispersion, essentially spreading of any material in a turbulent fluid is what we can call turbulent dispersion. And it has been very well established that the dispersion phenomena can be best studied by using a Lagrangian approach, where we follow the motion of infinitesimal fluid elements, or also called fluid particles or passive tracers in literature. And by definition, fluid particles have zero size and they move with the local flow velocity. So essentially they are just points moving with the velocity at that position. And the Lagrangian concept can be also extended to study effects of molecular diffusion and inertial particles, as you saw earlier in the session. And typically we look at motions of single particles, or we can look at relative motions between two or more particles. And one of the key motivations behind doing DNS is obviously to understand the universality, coming from Kolmogorov's hypothesis at high Reynolds number. And of course we cannot apply DNS to most of the practical flows that we encounter. So a lot of data produced by DNS goes into developing good models which are applicable to more practical flows. So when we talk about turbulent dispersion, there are two aspects from which we can look at it. So one is, we ask ourselves, given this material, how will it spread? And that's the most common approach studied in both experiments and simulations, where we introduce some set of particles at some initial time t equal to 0, and then track them forward with the flow velocity to some final observation time t equal to capital T. And this obviously is very helpful in understanding spread of anything in turbulent fluids. But from a practical point of view and a modeling perspective, it's often important to ask, how did this material come here? We look at some material and then we want to essentially trace it back to its origin. And in such a scenario, it's more relevant to look at their inverse history in time. So we start our observation time at some capital T, and then we trace them back to their initial locations or source of origin, essentially tracking them backwards in time. And this idea, without giving much explanation about it, is the critical idea in turbulent mixing when we are looking from mixing from a Lagrangian perspective. And for the nth moment of the scalar field, it can be derived by using backward statistics of an n particle cluster. And this idea is actually very simple. You just go back and you look forward or you look backward. It's just like a reversal of the frame. But it's actually very difficult to do because Navier-Stokes are time irreversible. So we cannot actually just integrate the Navier-Stokes in the negative direction to obtain what we want. The Navier-Stokes still have to satisfy from t equal to 0 to t equal to capital T. So this approach, so it's actually, like, without again going into many details, it's very difficult, and it's actually the details provided by DNS allows a very brute force post-processing approach, which can be found in the following paper. So giving a brief background about the methods and the parallel implementation. So we solve Navier-Stokes with constant density, where this F is some forcing term to maintain stationarity. And we are looking at isotropic turbulence in cubic domain using periodic boundary conditions. So essentially, we are doing FFTs. And we use a two-dimensional decomposition for our processor, for our domain. And we have essentially the approach to do the FFT is like take the FFT in one direction, transpose the data, and so on and so forth. So essentially, there are two global transposes which are done using all-to-alls, and one of them is in the row communicator and the other is in the column communicator. And for optimal performance, what we want is P row to be less than or equal to 32, because 32 is the number of cores available on one node on Blue Hours. And what it enforces is that now we still have the two-dimensional decomposition, but essentially one node on the computer has a slab of data. So the first all-to-all is always on the node. It never uses the network, so it's much faster. And we have been able to scale it up with the help from consultants using CoA Fortran and topology-aware scheduling, and on 8192 cube grid points using 256K cores, using this processor grid of 32 by 8192, we get like around 9 seconds per step. And using this DNS, some of the earlier findings that we reported earlier was based on the extreme events occurring at high Reynolds number, where extreme events essentially are localized and very rare regions occurring both in space and time, which have very, very extreme high rates of strain or rotation, essentially very high dissipation and entropy. And one thing which we found was that the structure of these extreme events, or one thing which was reported by Young and others in PNS, was that the structure of these extreme events is actually very different when you go to a high Reynolds number compared to what people have found at moderate Reynolds number. Like we no longer have the vortex filaments or the vortex tubes like encircled by dissipation sheets. It's more of a chunky structure appearing at high Reynolds number. And one of the key things is we need high Reynolds number to understand what is going on, and at the same time, since we are looking at small scale intermittency and things like that, we also need a very good resolution. And I guess that is one of the reasons why Blue Hours is so important for us. So one of the things that we want to look at is that how these extreme events affect turbulent dispersion. And many of the important applications where this is used is like in flame propagation and quenching, in combustion phenomena, or even in cloud droplet clustering. We know that the small scale intermittency plays a very big role. So coming quickly to the particle tracking portion of the work. So we initialize particles at time equal to 0 and then track them forward with Navier-Stokes. So we are first looking at fluid particles. So the rate of change of position is just given by the velocity at the position. Of course, the velocity is only available at n cube grid points, and the particle can be anywhere. So we need to interpolate in between the grid points to obtain the velocity. And to do so, we use cubic spline interpolation as reported by Young and Pope in JCP 1988. And the good thing about this is that it's 4th order accurate and twice differentiable, which is very important for looking at velocity gradients and acceleration, because they essentially like come from the derivative of the velocity. So at any given location, the interpolated velocity is given by this formula, where B, C, and D are the basis functions which depend only on the position of the particle. And the E, I, J, K are the so-called spline coefficients, which essentially is the velocity field transformed to do the interpolation. So for n cube grid points, we have n plus 3 cube spline coefficients. So as you can see that they don't really depend on the number of particles. They just depend on the velocity field itself. And it can be reused for other, so we can have multiple groups of particles using the same spline coefficients, but the basis function would be different. And the interpolation stencil is 4 points in each direction, so we need a total of 64 points to do the interpolation. So of course, the number of particles are also large and distributed among MPI tasks, and for these spline coefficients, they scale as the number of grid points. So we also have them decomposed into a pencil format using the 2D domain decomposition. And without again going into much details, they require 3 computation cycles and 2 transposes, very similar to how the FFTs are done. But in this case, since the number of points are not divisible by the number of processors, we use all-to-all Vs. And one of the challenges is how to interpolate, which I'm sure many people have come across before me. So particles, they keep wandering because of the physics, flow physics, and the neighboring grid points obviously keep on changing. So one of the approaches that we have been using for a long time is what we call the global approach, in which each MPI task is always responsible for the same set of particles. So regardless of where the particle is in the physical domain, the MPI task will always carry that particle. And what this means is that at a given point, the distribution of particle will probably look like this. Let's say we have 4 processors, and then we are looking at the particles held by P3. So now the domain or the spline coefficients it contains is just this subdomain, but the particles are actually scattered in the entire domain. So essentially what you can think is, as in what you can infer is that we'll have to do some kind of a collective communication to gather all the information from other processors to interpolate the velocity. And each processor will contribute what is essentially like a partial contribution for this entire summation based on the spline coefficients that it has. And then later on, we can do like a reduced scatter to gather all the information on the respective tasks. And the good thing about this implementation is that it's very generalized, and the particles can move any distance that they want in a given time step. And I'll come to that, why that is. And because of the number of particles being the same on each processor, the load balance is always uniform. But as we are using collective communication calls, they scale up very poorly. So they become very expensive at the petascale problem sizes that we are interested in. So one of the approaches that we came up to counter that at the largest problem sizes was using a local approach, which I guess I'll talk about it more. It's a very common one used in other work also, is that now each MPI task is responsible for a dynamically set of evolving particles such that the interpolation stencil is always locally available. Of course, so at any given time, the distribution looks like this task has this subdomain, and the particles are always like inside that region. So of course, for particles very close to the boundary, we need some kind of a communication to interpolate. And as the particle moves out of the domain, we transfer their control to the new respective MPI tasks. This may restrict how far a particle can move in a given time step, depending on how the implementation is done. So, but as I mentioned, that this is a very common approach, but I'll talk about how this becomes very different when we look at a very large problem size. So now, the typical layer to do the interpolation for particles near the boundary is to have ghost layers. And these ghost layers can be filled by doing like a send-receive halo exchange between the neighboring processors. But this ghost layer approach is not really feasible, as we found at the largest problem sizes. Now consider a 8192 cube grid using 32 by 8192 processors. So there are these many spline coefficients. So each processor has something like these many data points. And if you look at the third direction, it has just one data point in that direction. So if we want to maintain a ghost layer in that direction, we are looking at a pencil size which is like 5 to 6 times more than the original pencil size. So it's not really feasible to use a ghost layer approach. And even if, let's consider we are using the ghost layer approach, the number of grid points are so much larger compared to the number of particles at such a large problem size, is that for every 1,000 grid points, we have roughly one particle. So if we look at that in the three-dimensional space, we are looking at 10 points or more than 10 points in each direction before we encounter one particle on an average. So what we found is that this ghost layer approach is not going to help us at these problem sizes. So the idea is we want to keep the required data in the remote memory itself. We don't need to have ghost layers. We just fetch the data using one-sided communication when it's required. And what we found is that using CoA Fortran on CoA compilers was really good. So let me just briefly talk about CoA Fortran. So as you people know that CoA Fortran is a partitioned global space address programming model, and arrays are allocated, or co-arrays are allocated in the global space, and there is just an extra array index called, or the image index, where you can fetch data using one-sided communication. And it's currently, as far as I know, only fully supported on CoA compiler among all the big compilers on all the major supercomputers. And the best thing about it is that it's perfect for small message sizes. Like if you want to fetch small message sizes very frequently, it's actually much better than using MPI also, because MPI has more synchronization cost compared to CoA Fortran. So the idea is to declare these spline coefficients as a global coarray, and then you fetch the required spline coefficients directly from the remote memory. And this is still, the fetching is always going to happen in a local region, right? Because if I'm looking at a particle in a given task, the domain the spline coefficients required for interpolation is not going to extend like into 10 tasks beyond it. It will still be nearby. So it still exploits the p-gas locality. And I'll just briefly go through like a sample code. So if we declare what is the global array, and it has this co-array index, and then we loop over all the particles. Based on the position, we calculate these basis functions, and then this nested loop structure is for calculating the sum over all the interpolation stencil points. And since the domain decomposition in this pseudocode is in the y and the z direction, for every y and the z direction, we find some index and we fetch the data. And the data is continuous in the x direction, so we can fetch the entire row of data in the x direction. And we just based on the index, we just find the target rank, and then we provide that as the co-array index, and we just fetch the data. Now, the best thing about this is that if target rank is the same as the rank of that processor, then this is actually a local memory copy. This is not a remote communication. So it ordinarily takes care of both local and global memory communications or copying. And these are some of the performance results. So the first timings, they show the spline coefficients, which I mentioned, they don't depend on the number of particles. So what you're looking at is 3 different problem sizes going from 2048 cube to 8192 cube, and the number of processes are increased using the strong weak scaling argument, And whether we are looking at 16 million or 64 million, or whether we are looking at global or the local approaches, all the timings, they collapse. Now, of course, the weak scaling is not very good here for this case, because it's still all-to-all happening for this. But now if we come to interpolation, if we look at the older scenario, for 16 and 64 million, these cross, the blue and the red ones, they actually went up with the number of processors being going up, because we are looking at global collective communication calls being used. So they scale, again, very poorly. But now when we move to the local approach, what we find is, okay, it's not still perfectly strong scaling, but the scaling actually is holding up. It's actually going down with the number of processors. And just the interpolation cost is 2 orders of magnitude better than what we had earlier. And if we look at, say, 64 millions with 8192 cube, this last line of data, this timings are almost negligible. They are less than 1 second compared to this, what was some 50 seconds. And the total timing is essentially just this timing, and this is taking 5 seconds. So if we look at the overall timing, then the performance speed up is more 10x. And it's the good thing, another good thing about this is that it takes into account the Eulerian part of the code also. So when we look at the code, we are interested in combined improved performance for the Euler and the Lagrangian part. So coming at some results, so what are the questions we want to answer at high Reynolds number? So one of the important quantities looking at one particle Lagrangian statistics is this structure function, which should by Kolmogov's hypothesis scale as this, but there hasn't been concrete data to show this convergence completely at high Reynolds number yet. The trend is there towards, if you look at the data across all the Reynolds number, the trend is there towards these constant being 7, but there are still some unanswered questions. And then the next is how do these higher order structure functions scale? And then, so one way of also looking at what I was talking about the extreme events before is to look at these structure functions conditioned on the extreme values of dissipation and entropy. So I guess I'll quickly go through it. So what I'm showing here is the non-dimensional fourth order structure function conditioned on the y, which can be the dissipation or the entropy. Now these data, the data is still undergoing post-processing, so we don't have the data up for the extreme values of dissipation, but we can look at the trends that what happens when the dissipation and entropy increases. Well, I guess the structure for dissipation is still very monotonous, but we can start to see these vortex trapping zones coming up when the entropy goes very high. And then looking at relative dispersion, we want to study the relative motion between two particles. So if we define the separation vector as this, then conditioned on the initial separation, we can define power laws for different regimes. And one of the most important ones is the one which happens in the initial range, also called the Richardson scaling, where the relative dispersion grows as t cube. Now this has been a very hot topic of investigation in literature, and one of the key things that is known for a long time is that it's forward and backward different. Like the Richardson scaling scales differently for the forward dispersion versus the backward dispersion. So one of the things that we wanted to do was investigate that, and what you're seeing is plots of the dispersion versus time normalized by the Kolmogorov variables for forward and backward for different initial separations at two different Reynolds number. So what we find is that small time and large times they are similar, but at intermediate times the backward dispersion is much faster. And one of the ways to quantify that is to look at the so-called cube local slope, where we essentially take this expression, take the cube root, then take the derivative to isolate this g. Like if this scaling holds, then this number or this slope would give a plateau at g. And we look at different Reynolds number data at different initial separations, and we plot them together. And what we find is that for the forward case, we get really good convergence at about 0.55, and this is at r lambda of 1000, the Taylor scale Reynolds number. And comparing this to the results by Sofford and others at r lambda 650, it's in very good agreement. But for the backward case, we find that the trend towards the convergence is there, but it's still not perfectly converged. We are estimating about 1.5, but we still need higher Reynolds to see a perfect convergence. And more details can be found in this paper. And just the last couple of slides. So one of the extensions of this is to include the effects of molecular diffusion, and that's by adding this Brownian motion term to the equation of the particles. And this is, as I mentioned, the backward statistics of so-called molecules are going to be very important in studying turbulent mixing. Now I don't have a lot of results here, but if you're interested, you can look up the results in the paper. And this work can also be extended by looking at multi-particle clusters of 3 and 4 particles. And I guess a key thing is why blue auras. So turbulence is a grand challenge in both science and high performance computing. We are looking at a wide range of unsteady, non-linear, three-dimensional scales and different flow physics also coming together. And high Reynolds number with better resolved small scales is very important. And to achieve both of them, we need simulations of very large size. And Blue Orders is one of those machines which can help us, or is helping us already to do so. Like if it was not for Blue Orders, then I don't think we would have been able to do the largest simulations that we have done so far. And concluding remarks is that with the help of Blue Orders, we have been able to do some very large scale Eulerian and Lagrangian simulations to understand the process of turbulent dispersion in a forward and backward reference frame better. And we are still doing some ongoing work with the extreme events on the effect of extreme events on Lagrangian intermittency. And in the long term, we plan to include more complex physics like high Schmidt number mixing and electromagnetic forces and rotation effects in our work. Thanks a lot.